Right now, astrophysicists are staring at data from the James Webb Space Telescope that is causing, genuine panic.
Yeah, panic is definitely the right word for it.
We are talking about images that, according to the fundamental laws of physics that we all learned in school, they just shouldn't exist. If this data holds up, the first page of every history book on Earth, that neat 14 billion year timeline of the Big Bang,
Right.
it might be a complete fabrication.
It really is the ultimate scientific crisis right now because, we pointed the most advanced infrared telescope ever built into the absolute darkest, oldest corners of the cosmos.
Right, looking for the beginning.
Exactly. We were fully expecting to see the chaotic, messy beginnings of the universe, but instead we found structures so massive and mature that they threatened to completely break the standard model of cosmology.
Which is wild. So the mission for our deep dive today is to examine exactly what this telescope found at the edge of time and why it is physically impossible under our current understanding of physics.
And we'll look at the radical theories scientists are proposing to fix this.
Yeah, from cyclic multiverses to eternal realities. We're going to get into how we actually got here. But to understand the sheer scale of the problem, we first have to look at how the James Webb Space Telescope, the JWST, actually captures these images.
Right, so we are dealing with a phenomenon called cosmological redshift. Because the universe is expanding, the actual fabric of space itself is stretching out.
Okay.
So when light from the earliest days of the universe travels toward us over billions of light years, that light gets physically stretched along with space.
Right. So I was reading about this, and it's basically like drawing a squiggly wave on a rubber band and then pulling the rubber band, right? The wave stretches out.
That's a perfect analogy, yeah.
So the light emitted by these early stars might have started as visible light or even ultraviolet light. But by the time it reaches our solar system, the wavelength has been stretched so far that it just drops out of the visible spectrum entirely.
Exactly, it drops into the infrared, which is exactly why the Hubble Space Telescope couldn't see these earliest structures.
Because Hubble mainly sees visible light.
Right. JWST, on the other hand, was specifically engineered with these massive gold-plated mirrors to capture that incredibly faint, deeply red-shifted infrared light. The whole goal was to look back to a period we call the cosmic dawn.
And that's, what, roughly 300 to 500 million years after the Big Bang?
Give or take, yes. And because light takes time to travel across the universe, looking at an object 13 billion light years away means you are seeing it exactly as it existed 13 billion years ago.
So the JWST is essentially a time machine.
Oh, absolutely. It's a time machine. And based on the standard lambda CDM model of cosmology, which is the mathematical backbone of the Big Bang astrophysicists, knew exactly what this time machine was supposed to show them when they looked at the cosmic dawn.
They thought they knew anyway.
Right, yeah. They expected to find the earliest precursors to galaxies, just sparse, chaotic clouds of neutral hydrogen gas that were slowly, very slowly being pulled together by gravity.
So just a bunch of dust and gas.
Yeah, and they expected to see the very first generation of stars, which we call population 3 stars, just beginning to ignite. These would be massive, really short-lived stars made entirely of hydrogen and helium.
Because heavier elements simply didn't exist yet, right?
Exactly. The expectation was just a messy, dark, formless nursery.
But, and this is where it gets crazy, the data that came back didn't show a nursery at all. JWST found fully formed, highly structured galaxies holding tens of billions of solar masses.
It's completely staggering.
Some of these galaxies are roughly the mass of our own Milky Way, just sitting there a few 100 million years after the Big Bang. To use an analogy that's actually straight from the astrophysics papers trying to grapple with this, it is exactly like walking into a hospital maternity ward, looking into a newborn's crib, and finding a fully grown 80-year-old adult sitting there.
Just hanging out in the crib.
Yeah, wrinkles, gray hair, reading the newspaper. It's a profound physical impossibility.
It really is. And the anachronism of the 80-year-old in the nursery, it gets to the very heart of the mechanism that is currently breaking our models.
Because of how long it takes to build a galaxy.
Exactly. Under the standard model of galaxy formation, creating a galaxy of that mass requires a really rigid, time-consuming sequence of events. First, dark matter has to pool together to create a gravitational, well, what we call a dark matter halo.
Okay, so like a foundation.
Yeah, this halo acts as the invisible scaffolding that can eventually pull in that chaotic hydrogen gas.
And pulling that dark matter together alone takes an immense amount of time, doesn't it?
Oh, it takes hundreds of millions of years just to build the scaffolding. And only then can the gas condense enough to ignite that first generation of stars we talked about.
Right.
Then, those stars have to live out their entire life cycles, explode in supernovas, and seed the surrounding space with heavier elements, what astronomers call metallicity. Carbon, oxygen, iron, things like that.
And then a second generation of stars forms from that enriched gas.
Right, and then a third. This entire process, just building the complex structure of a massive galaxy, it requires roughly 1 billion years minimum.
1 billion years.
Mm.
Yet JWST is capturing images of these massive galaxies at what we call redshift Z equals 10 or Z equals 13, which correlates to just a few 100 million years after the beginning of everything.
Yeah.
So we are seeing the finished multi-generational product before the factory was even built.
Which leaves the physics community basically staring at a brick wall. They call it the impossible early galaxy problem. The mass of these galaxies literally exceeds the available baryonic matter, the normal visible matter that our models say should have even existed in those dark matter halos at that point in time.
Okay, wait. Before we just throw the Big Bang out the window entirely, I have to play devil's advocate and push back on this.
Sure, go ahead.
Isn't it significantly more likely that our models of galaxy formation are just, I don't know, too slow? Like, why jump straight to the fundamental timeline of reality is a lie when maybe early supermassive black holes just supercharged star formation? Or maybe the gas just condensed way faster than we calculated.
Well, that is absolutely the first line of defense for cosmologists right now. They are desperately trying to find a way to accelerate galaxy formation without breaking the entire timeline.
Okay, so what are they proposing?
Some propose that early black holes created massive feedback loops that rapidly compressed gas into stars. Others suggest that stars in the early universe formed with vastly different mass distributions, which would make the galaxies appear more massive and mature than they actually were.
But, I mean, those sound like increasingly desperate tweaks to save a failing model.
They are. They really are struggling because the lambda CDM model is incredibly rigid. It's a tightly interlocked system.
Right, you can't just change one thing.
Exactly. If you change the rules of how fast dark matter clumps together or how fast gas cools to form stars, it doesn't just change the cosmic dawn. It ripples forward and breaks our models of the modern universe.
Oh, wow.
Yeah, if galaxies could form that incredibly fast back then, the universe today should be wildly different than what we observe. We should see drastically different distributions of matter everywhere.
So you pull the thread on early galaxy formation, and the entire sweater of the standard model just unravels.
That's exactly it. Furthermore, tweaking the early formation rate clashes violently with the cosmic microwave background radiation, the CMB.
The afterglow of the Big Bang itself.
Right. The CMB provides a highly precise map of the universe's density fluctuations just 380,000 years after the Big Bang. And that CMB data sets a hard limit on how fast matter could have started clumping together.
Yeah.
So we are trapped. We're trapped between the CMB data, which says matter was still incredibly smooth and diffuse, and the JWST data, which shows massive, dense galaxies existing almost immediately afterward. There simply isn't enough time between the two observations for the physics to work.
That is wild. So if the physics of galaxy formation cannot be accelerated enough to explain the JWST images, we are literally forced to confront the timeline itself.
We are.
The 13.8 billion year age of the universe is the foundation of modern science. But if these giant galaxies are existing in a time period where they cannot physically exist, then the time period has to be wrong.
And renowned theoretical physicists are stepping forward to address this exact crisis right now. When a foundational theory makes a prediction, and the highest fidelity data we have completely contradicts that prediction, the theory must be dismantled.
Right.
The data from James Webb is actively threatening the absolute laws of cosmology. We are facing the terrifying prospect that the Big Bang, the idea of a singular origin point for all reality might just be fundamentally flawed.
Which opens a massive, terrifying void in our understanding of existence.
Yeah.
Because you can't just dismantle the Big Bang and leave a vacuum.
No, you definitely need a replacement.
Right. So what are the actual mechanical alternatives being proposed to fill that void? Like, if there was no Big Bang, how do we explain the expanding universe and the presence of these ancient galaxies at the edge of our observational limits.
Well, there are two revolutionary or perhaps heretical models that are gaining immense traction in theoretical physics right now. The first is the cyclic multiverse.
Okay, the cyclic multiverse.
Yeah, it's sometimes referred to in various frameworks like conformal cyclic cosmology or the ekpyrotic model. The standard Big Bang is a linear vector. It has a definitive start and expansion, and eventually it ends in a heat death.
A one-way street.
Exactly. But the cyclic model discards that single origin point. Instead, it proposes that our universe undergoes continuous, infinite cycles of expansion and contraction.
So it's less like a firework going off once and fading into the dark, and more like a Newton's cradle.
Oh, I like that, yes.
The energy doesn't just dissipate forever. Gravity, or, other fundamental forces, eventually halt the expansion, pull everything back together into a big crunch, and the sheer density and heat of that collapse trigger a massive rebound, a big bounce.
It's a big bounce.
The energy swings back, condensing and violently expanding again, recycling the same cosmic material over and over.
The Newton's cradle is a highly accurate way to visualize the mechanics of it. In a cyclic multiverse, the quote-unquote Big Bang we observe wasn't the beginning of time at all. It was merely the bounce from the previous cycle's collapse.
Wow.
And this elegantly solves the impossible early galaxy problem. Because if the universe has gone through these cycles countless times, it is entirely possible that certain structures, like dense pockets of dark matter or even black holes from the previous cycle, they actually survived the bounce.
Wait, really?
Yes.
Meaning the JWST isn't looking at an 80-year-old who somehow aged instantly in the newborn nursery. It's looking at an 80-year-old who just walked into the nursery from the previous room.
Precisely. The material was already matured in a previous cycle of the universe.
That dramatically reshapes how we view reality. But you mentioned two alternatives. If the cyclic model relies on a bounce, what is the second theory?
The second major alternative is the steady-state universe.
Okay.
And this idea actually predates the dominance of the Big Bang theory. It was originally championed by physicists like Fred Hoyle in the mid-20th century, well before the discovery of the cosmic microwave background kind of pushed it out of favor.
Oh, interesting.
But in light of the new JWST data, modified versions of the steady-state theory are absolutely being resurrected.
The steady-state theory always sounded to me like an infinite ocean. Like if the Big Bang is a singular explosion, the steady state is a reality that simply is. It always has been, and it always will be.
That's a good way to look at it.
But how does that physically work? Because we know the universe is expanding, right? Hubble proved that a century ago. So if the universe is eternal and constantly expanding, shouldn't all the matter eventually spread out so far that the universe becomes completely empty?
Well, that is the central paradox the steady-state model has to solve, and it does so through this really fascinating mechanism of continuous creation.
Continuous creation.
Yeah, to maintain a steady state, meaning a constant density of matter over infinite time, despite the expansion of space-new matter, must be continuously generated in the voids between the retreating galaxies.
Wait, just spontaneously appearing out of nowhere.
Basically out of the quantum vacuum.
Seriously.
Yeah. Quantum field theory already allows for particle-antiparticle pairs to pop in and out of existence all the time. The steady-state model proposes that a slow, constant trickle of new matter, mostly hydrogen, is perpetually generated by the expansion of space itself.
That is mind-bending.
Isn't it? As galaxies drift apart, new hydrogen fills the gaps, slowly pooling together over eons to form new stars and new galaxies. It creates a universe that is dynamic and expanding, but fundamentally unchanging in its overall composition.
So if we're in an infinite, eternal ocean with continuous creation, finding an impossibly mature galaxy billions of light years away is no longer a crisis at all.
Not even a little bit.
Because time isn't a straight line that started 13.8 billion years ago.
Yeah.
If the universe has existed eternally, then there is no such thing as a cosmic dawn.
Exactly. Every era of the universe looks roughly the same. There are mature, fully formed galaxies everywhere you look at every stage of development, regardless of how deeply you peer into the infrared spectrum.
The steady-state model just eliminates the concept of early entirely.
It does. There is no beginning for these galaxies to be too early for.
Yeah.
The universe JWST is observing is just a local patch of an infinite expanse that has been churning out galaxies forever.
You know, exploring these mechanics, it really moves us away from just talking about gas and dark matter halos. It forces us into something far more profound.
It really does.
We're hitting the philosophical core of what this deep dive is actually about. Because the deeper JWST looks into the dark, the more it fundamentally shatters the human ego.
Oh, the ego of modern cosmology is highly evident in how we treat the Big Bang. I mean, we mapped the cosmic microwave background, we calculated the expansion rate with the Hubble constant, we wrote dense textbooks, and we handed out Nobel Prizes.
We really patted ourselves on the back.
We did. We built an incredibly rigid mathematical fortress based on the comforting idea that we had the grand story of the cosmos figured out. We put the entire universe in a neat little box labeled 13.8 billion years.
And Cosmos just handed that box back to us completely crushed.
Yeah.
The arrogance was assuming that just because our math worked for the local universe, it must apply to the very edge of time. But this proves that science isn't just a list of solved facts for you to memorize. We talk about physics as if it's a finished puzzle and we are just hunting for the last couple of edge pieces.
Right, right.
But JWST just pointed its mirrors into the deep past and proved that we aren't even working on the right puzzle. We might be in a completely wrong room.
That realization is honestly epistemologically terrifying. It is the vertigo of standing on the edge of a cliff in the dark and realizing the drop is infinitely deeper than you thought.
Yeah.
But, it is also the supreme beauty of the scientific method. It is self-correcting, regardless of how painful that correction is to our established paradigms. We have to follow the data.
Always.
If the data dictates that the Big Bang cannot account for the mass of these early galaxies, we must be willing to abandon it for a cyclic model or a steady-state eternity.
Which leaves us with a totally different perception of reality than the one we learned in grade school. We went looking for the baby pictures of the universe, and we found ancient, towering structures that completely defy the laws of time. We learned that the universe is not obligated to make sense to our current level of understanding.
Well said. And as we synthesize the implications of these impossible early galaxies, it raises a final, really provocative thought regarding how we view the universe. Well, if we ultimately discard the Big Bang, if the cosmos is truly a Newton's cradle of infinite bounces or an eternal, steadily expanding ocean, does that mean the very concepts of beginnings and ends are just human biological illusions?
Oh, wow. Because we are biological creatures. We're born, we live, and we die.
Yeah.
We have a clear beginning and a clear end.
And because of that biology, we inherently demand an origin story for everything around us. We assume the universe must operate on the exact same timeline as a living organism.
Right.
But what if time doesn't care? What if we have been projecting the biological limits of our own mortality onto a cosmos that is fundamentally immortal?
Are we projecting our own birth and death onto a universe that has never experienced either? That's exactly the kind of question that forces you to look up at the night sky completely differently.
It really is.
The sheer scale of what we don't know is thrilling. So, to you listening, keep questioning the physics you take for granted, because the 80-year-olds in the cosmic nursery are still out there, waiting for us to catch up to them.